Greetings, traveler. I'm the Calculus Cleric, and today we're working with more infinite series. So, the specific pattern is to find the total length of the infinite zigzag path. Now, I kind of gave it away what we're going to do here, but basically, let's break this problem down. So, over here is our figure. It looks to be a large triangle, and these angles over here are in radians, pi fourths, which is 45 degrees. And if this is 45 degrees and this other angle is 45 degrees, now triangle sums up to 180. And you might know this 45, 45, 90 degree triangle, making this a right triangle. Now it also gives us the side length of the first zigzag, which is 1. And it looks like they want us to find these side lengths for each subsequent triangle an infinite number of times. Now, if we look more closely at this problem, we'll see that this leg that they're attempting us to find is also the hypotenuse of the next triangle. With these two over here being the angles and this being the right angle. And then over here is the same thing, right angles over here. And then we have the hypotenuse, which I'll just call capital H. And then hypotenuse, right angle. And we notice that these zigzag paths are actually just the hypotenuses of all the triangles, while also being the leg of the previous triangle. But let's just stick with all of them being hypotenuses because that'll make our life so much easier. Now, let's go figure out what the other side lengths are. Now that we know that side length is 1, we know that by 45, 45, 90, this is isosceles triangle. And by the Pythagorean theorem, a squared plus b squared is equal to c squared. In our case, both sides are the same length, so we can call both of them a squared. 1 squared is just 1, 2 a squared. So our a length is equal to 1 over the square root of 2, which is also equal to root 2 over 2. They're both the same thing. You don't have to do it as root 2 over 2. You can keep it as 1 over root 2. But I'm just going to do root 2 over 2 as my a. Because we have found out the side length of this triangle, we have now actually figured out the hypotenuse of the next triangle, because this is the hypotenuse of the next triangle. So, by that logic, we can continuously use the Pythagorean theorem to find us the side lengths of the next descending triangle in order to find the hypotenuse of the next infinite number of triangles. Now, we're not looking for the side lengths of all these triangles, rather, we're trying to find a general pattern because there's no way for us to calculate all the side lengths of an infinite number of triangles. We'll be sitting here forever, quite literally. Okay, so armed with this knowledge, this side is root 2 over 2. Now let's find the side lengths of the other triangle. Once again, we use the Pythagorean theorem. Let's call this side length b. B squared plus b squared. So 2b squared is equal to root 2 squared is 2, 2 squared is 4. Multiply both sides by 1/2. B squared is equal to 1/4. So then square root both sides, giving us b is equal to 1/2. Although you might say technically it can also give us negative 1/2. Remember that this is side lengths of a triangle, and we can't have side lengths of a triangle that are negative. Otherwise, you won't really have a triangle. Okay, moving on. So our b length is 1/2. And how do we arrive at that? Well, we squared root 2 over 2. Let's go for one more triangle, and then I'll tell you my hunch for the pattern. And half squared is equal to, let's call this side length c. C squared plus c squared, 2c squared is equal to 1/4. C squared is equal to, multiplied by 1/2, 1/8. And then square root of 8. And my hunch is, well, let me cube root 2 over 2. This cube, so it's 8 all over. So that cubed is 2 root 2. So that's 1, 4, followed by root 2. Okay, so that's root 2 over 4, root 2 over 2 cubed. Okay, maybe it wasn't the best decision to use root 2 over 2. Anyways, let's rationalize this. Root 8 over 8. Root 8 is equal to 2 root 2 all over 8, which is root 2 over 4. Okay, that was a very messy train of thought, but basically what I'm attempting to prove here is that when you cube root 2 over 2, you'll get the same answer as the third side length c, and that's my hunch for my answer actually. Okay, so basically that's the pattern that I'm using, so where a, b, and c is the first, second, and third term respectively. And my hunch is if I use root 2 over 2 and then I put that to the nth power, it will give us the terms for whatever n value is plugged in. So if I plug in 2 to my n value, give me the second side length, b, which is indeed true when I square root 2 over 2. As we saw earlier, this gives you 1/2 because 2 over 4, 1/2. And then, as I proved previously, it also works for when you plug 3 in. And this will also work when you plug in 1, and it will give us the first side length. And conveniently, if we plug in 0 for the initial side length, we'll get 1. But because it's an infinite number of zigzag paths, I can call this an infinite series because we need to add all their lengths together because they're asking us to find the total length. And so this is an infinite series since the paths themselves are infinite. And we start at n is equal to 0, so we can get that 1, the initial side length. Now, this is an infinite geometric series, and this will converge out to some sum because root 2 over 2 is less than 1. So using the basic formula for geometric series, this is what it is when n is equal to 0, where c is some constant that is in front of our series, and r is the base of the nth exponent. Okay, so c, well, I don't see any c value in here. That's because it's just 1. So 1 can hide in front of literally anything because 1 multiplied by anything is just the other number. So our c value is 1. Substitute 1 in, and then 1 negative, and then our r value is the base, so that's root 2 over 2. So solving this out will get us 2 negative root 2 all over 2. And then we flip that, which gives us 2 over 2 negative root 2. And we can leave it like this if we want to, or we can rationalize this. We don't have to, but I'll just do it for free. 2 plus root 2. So you multiply it by its conjugates, which will give you 4 plus 2 root 2 all over. This is a negative b, a plus b type of situation. So it's a squared minus b squared, which is 4 minus 2. And let me give myself some more real estate, which is equal to 4 plus 2 root 2 all over 2. 4 minus 2 is 2. And then we can simplify that. So that's 4 divided by 2 is 2, plus 2 divided by 2 is 1. So 2 plus root 2 is our final answer for the total length of the infinite zigzag path.